Okay, so in this direction, go ahead.
Yeah, well, thank you, and like everyone, I want to thank the organizers for inviting me to come here. It's the first time I'm back in Seattle since before the pandemic, so it's very nice to see that everything is still very much the same. So, like previous talk, I'm also sort of, let me go back one slide here, like odd in this week talking about something very low energy, and also in this case like very few particles. So it's like sort of at the opposite end of this, but I hope this is going to be interesting. Before I start, I want to acknowledge the people I'm working with on this topic. Particularly, Bhavani is a PhD student at TU Munich. He contacted me in 2020, looking for theorists who can do this sort of calculation that I'm going to show you. And the calculation got expanded, including these people in Pisa here, Michele Vagliani, Alejandro Kievsky, Laura Macucci, and some other people. So I'm going to show, this is a collaborative effort. I'm going to show results of my theory calculation. I'm going to point to what's coming out. So this paper, it's in internal review under Ellis. This is part of the Ellis collaboration. I'm going to zoom in on the stuff that I was doing in particular. So the idea is this femtoscopy. It was mentioned a little bit last week. If we have like two heavy ions, or it could actually be two protons too, you get the same kind of information out, and you collide them, and I've learned that you should make that like a little pancake and fast. So they collide in a very, very high energy collision, and there's a bunch of stuff coming out. And experiments like Alice or Rick, you can measure these things. You can look at pairs of particles. So in this case, specifically, what I want to talk about is pairs of protons and deuterons. So they can identify even light nuclei in the spectra. And then even though this is a very, very high energy collision, if these particles have a low transverse momentum and the detectors are such that you can resolve that, you can actually learn something about the low energy physics of these particles. This is this idea of femtoscopy. So we can study the interaction between those particles, low energy interactions, potentially from these heavy ion or high energy collisions. Like I said, it doesn't need to be these heavy nuclei here. So you can study nuclear and hypernuclear interactions. I want to emphasize the hypernuclear because that's part of the motivation. Before I come back to that, just the basic idea in one slide for a very, very simple setup is that consider a two-hadron system with a low relative center of mass momentum that we call K. We say, let's assume it's a two-body system. We have a scattering wave function that describes these two particles at that relative momentum. Then there's this thing called the correlation function. That's basically the wave function squared weighted with a source function that's usually taken to be a normalized Gaussian. So you're assuming that you're creating these particles and then they're propagating out, and there's a final state interaction, which is described by this wave function.
You assume isotopic emission to start with?
Yes, I believe that's assumed, but then when you connect this to experiment, and the way this goes back to these older papers here, is you're looking at ratios of correlated versus uncorrelated pairs. I think you're correct for acceptance and so on.
Yeah, but from the theoretical point of view, your source is isotopic.
Correct, and then we're looking at partial waves. So this correlation function is going to be, in my formalism, you can do it in 3D, but in this formalism, it's summing partial waves. Assuming it's isotropic, that's correct.
And the source is also time independent, I guess.
The source is a little bit mysterious to me. So I think they take an assumption of when these things form. So in the analysis, they're looking at this formation time, but I think effectively the source becomes time independent. It's a Gaussian, but this is an assumption. Also the size of this thing, I'm going to come back to that later. So from the theory point of view, so as a theory, you can define this. So I'm happy with being on the theory side of this. So if there's no interactions, then just from flux conservation, this correlation function should go to 1. So a deviation from 1 modulo detector, acceptance, identification. So all of these things in the experiment have to be corrected for, but from the theory point of view, deviations from 1 encode the properties of the interaction.
Or quantum statistics, right?
Quantum statistics is important. It's going to be one part of the talk today because we have 3 nuclei.
But it's not an interaction.
No, but it's
And it gives
part
you a
of the
correlation.
dynamics. It's part of the dynamics. It gives you a correlation. Yes. And I'm gonna come back to exactly that point.
So is this understood in the sense what you asked, the three-body, you said a three-body panel?
He said 3 bodies. I'm just
It's a
saying, just,
proton
if you have
difference.
if you have even just 2 bodies, if you have a pair of identical particles, they'll have correlation. This correlation function will not just be uniformly 1, just because of the, exchange symmetry of their wave function.
At high energies, though, it should still go to 1. That's actually the probe. So at the low energy regime, I think you're right. If you anti-symmetrize, you get the signal from that alone. That's correct. And Michaela has done that sort of calculation, just taking Coulomb plus anti-symmetry. It's a little bit tricky because if you're saying you anti-symmetrize, but they're not interacting, like really you can't separate those two things theoretically. Either you do both or you do neither, but
you could study the same correlations within a jet. Then you will definitely know there is correlation.
I think that's how they do this. So when they're looking at correlated
Then
versus
you can look
uncorrelated
at
pairs.
comparative study. You can look at the same 2 final states. When you're looking inside a jet, the leading particle in the jet and the next to it is leading. And then at low energy, what you're doing is just very small energy.
Smaller,
Just 2,
yeah.
And then there is no correlation. You can know for sure there was correlation. There is no correlation.
No, you can also mix events.
That's what they do. They mix events. So this ratio is like the numbers you get from a single event compared to like getting the same from like a mixed events. Yeah. But I'm really not the expert on the experimental side. I have to say this is my very like bird's eye
Why
understanding.
would you especially interested in PD?
And come to this.
Any other
So in general, we can access these things. They can not only measure nucleons, they can also measure hyperons. And the hypernuclear interaction is something that's relevant for equation of state, neutron stars, and so on, but it's very poorly constrained because there's not so many experiments to date, scheduling experiments with hyperons. There's going to be more of that in coming years, but still, this is a very unknown part of the nuclear interaction. And one of the main motivations is that we can use these fantastically things to actually constrain that interaction. To make sure that we do that well, we should first make sure we understand what's going on. And the nuclear interaction, especially at low energies, there's tons of data, right?
The PD is constraining this interaction better than PP, for example, which is not safe.
No, the PD is interesting because we are having a 3-body system.
Oh, you're looking for 3-body.
PP has been
You
done.
take the simplest 3-body, which is 2 + 1.
Yes.
That's the idea.
Yes. They have data for PPP. Theory can also calculate, like I'm going to show Proton-deuteron too, but they can't see the neutrons, so there's not so much interesting experimental data to compare to. But yes, so we're doing PD because it's the simplest 3-body system with the 2-body factors. Correct. And we're looking at neutrons primarily to make sure we understand what's going on, because that we have plenty of other data to constrain the interaction, and then we should better be describing the experiment before we can say we get something about an unknown interaction out of the same experiment. So that's the line of thought for the motivation. Okay, so the outline is, that was my intro, and then I want to take you a little bit through how we do this calculation. So the middle part here is getting gradually a little bit more technical, but I'm going to come back to results at the very end. So I tried to set this up sort of like a lecture, and I hope the level is so that you can get something interesting out of that. And then at the end, I'll discuss the results. So part 1 is EFT. We've heard a little bit about it. You mentioned it briefly, and we heard more about it last week. So for those of you who maybe joined some of the talks virtually last week, you've seen something about it, but I'm going to show you an introduction about this, specifically about this Pineless EFT, because we're looking at very low energies. So my sort of propaganda slide that I like to show is this picture here, the general idea, and I don't need to be going through this very long because we've seen this already today. You can start with QCD, or if you want, you can put a molten lava core here and string theory maybe, but anyway, there's something complicated.
Let's fill the garbage.
I didn't say that. You have something that's at low energies. QCD is very complicated. That's the basic idea, because it's non-perturbative. You have confinement, you have all of that, but we can systematically connect to that. So as we change our degrees of freedom from quarks and gluons to nucleons and maybe mesons, we grow an effective theory out of this. In principle, the underlying theory constrains the unknown parameters of the lower resolution theory. There's some work being done where you actually extract low energy constants of the EFTs from lattice QCD, but for the most part, the EFT today is still constrained by experimental data. And then you can grow more effective, like also in terms of the methods, can be exact few body methods, such as the ones that I'm talking about today. You go into more effective descriptions. This might be, say, a shell model or a couple cluster. And then if you have something like a halo state, you have again an effective few body picture. And then you have like mean field descriptions, DFT and such, go to like more and more nucleons. But the idea is from QCD, we get an effective description, and which degrees of freedom we use depend on the resolution scale of the sort of physics that we want to describe. Because at every resolution, there's arguably one best or most effective way, I wouldn't say best, but most effective, efficient way of describing the physics, and they can be systematically connected. So zooming in a bit more on these EFTs, as I said, the degrees of freedom, they depend on the energy scales. If we just talk about nucleons and maybe mesons, we can look at the parameter space here as a function of the pion mass, which in nature is fixed at this line, around 140 here, but which lattice QCD can and does vary, mostly out of necessity, but also it's sort of fundamentally interesting to see how does nature change. Because QCD has basically only the quark masses as essential parameters. And then as you vary those, you can probe this direction. And you have like some, arguably maybe for any given thing you're looking at, maybe not one unique scale, but some typical energy scale. And we say like a typical QCD scale is something like the nucleon mass around 1 GeV. And then there can be low energy scales like nuclear binding energies that are typically much lower. Depending on where you are in this plane, which theory works, like there's overlapping regimes of applicability, varies. So chiral EFT is what we've heard about today already. This is within this set of theories that have nucleons and mesons between them. The one that's assumed to have like the largest range of applicability spends the largest area in the surface here. As you lower the energy, if you're looking at this picture, it's maybe better. As you look at very low energy, you're not resolving these pion exchanges. Just like in chiral EFT, you're assuming that you're not resolving exchange of heavier mesons because it's very short range, exactly what we've seen in the first talk today. So if you go to lower and lower energies, you have this. If you go to these cluster states, maybe you can even not resolve to leading order the cluster substructure, and then you put all of those things that you don't resolve in. That's the higher order interaction. So systematic. Nothing is eventually missing, but you're trying to put in the leading order what's most relevant. And then you can go like have effective theories, rotations, vibrations. Thomas Papenbrock collaborators have done that, for example. And this is just the same point I made before. So for the purpose of this talk, I want to talk about Pineless EFT. I do want to say, like, what's the general idea? Like, how do we do this in practice? This is why I have this slide here, which is sort of connecting to the stuff that I showed. So at the very beginning, if you don't know what to do, you have a physics problem, you want to use a nuclear physics problem, you want to use an EFT. You would start with like identifying what's the relevant symmetries that we have. At low energy, that's typically Galilean invariance, so we have relativistic boosts, rotational invariance, so on. Then maybe chiral symmetry or isospin, just as the remnant of chiral symmetry. And when I've got gauge symmetries, if you couple to external currents and so on, you identify the low and the high energy scales in your theory. And I'm going to come back to that on the next slide to identify what are the scales. And as I said, you to identify like what's the typical momentum scale for a given process. So it can be as simple as a binding momentum for the deuteron. We know the relevant scale is around 50 MeV because that's the binding energy compared to converted to a momentum scale. In heavier nuclei, not so easy to answer. Could be something like the binding per particle, could be a Fermi energy or something. Anyway, you have to make a choice. And then you can test your theory. Does it fulfill the expectations after you've made a choice? The high energy is a bit easier. It's like the physics, the lowest scale of course, describing physics that you're not describing directly. Say like the rho mass in chiral EFT, because you don't have rho mesons. So that's something where you would expect the high energy scale. Question? And then it's a field theory, you have to put a regulator usually because diagrams will be divergent. So you have to regularize and renormalize. Renormalize is closely related to how you fix your parameters. It's an EFT, you have a bunch of unknown couplings. After picking a cutoff, you would fix those couplings by some renormalization condition. Say you have like a set of input data which you demand that you should describe. And then as you vary the cutoff, your coupling will change because you just have a running coupling as in any EFT, in any field theory. And then amplitude here, that can be anything. It can be, say, a binding energy, which comes from an amplitude as a pole in the S matrix, if you want to talk about it that way, but it can also be a scattering amplitude. For the purpose of today, it's useful to think about that. The EFT expands this systematically in this ratio. So typical, your low momentum scale over the high scale. So this is a parameter less than 1. If you want a theory, that makes sense. To some index, and you're summing this. If you truncate this, then you're calculating up to a given order. And then you have, I don't want to dwell on this too long, you have low energy dynamics. These are sort of Feynman diagrams in a non-perturbative setting, I should add, and I'm going to talk about that more. So this F is Feynman diagrams, and the low energy constants are these gamma nu here. And then importantly, you have a prescription, because in the effective Lagrangian, you just write down everything that you can have that satisfies your symmetries, but you have to order them somehow by importance. That's a process where it becomes non-trivial and where people discuss and where people disagree. But in principle, you have a guideline how to relate powers here in this expansion. So this is the power that determines the order of the expansion for the observable, how you relate that to the terms in your Lagrangian, of which you have infinitely many. So that's what's called power counting. It's a choice you have to make. And then if you want a field theory that is properly renormalized, you would also typically check that this T here that you predict becomes independent of your regulator up to inverse powers of your regulator. And then that should become smaller and smaller as you go to higher and higher orders, the power of these correction terms here. Okay, so let's talk about these scales. And I mentioned this before in chiral EFT. It's built around the chiral symmetry that QCD would have if the quarks were massless, and then the pion mass is something that breaks this explicitly, but it's small. The pion is much lighter than all the other hadrons, which led to this approximate symmetry. And then the power counting for chiral EFT is set up in such a way that you identify your low energy scale with the pion mass. So you're saying that the theory is constructed to describe momenta around the pion mass, so something around 140 MeV. And your high scales are, depending on how you set it up, could be nuclear mass, rho mass, or there's like arguments where it would be related to the pion coupling. In any case, this ratio is what gives you your expansion parameter, like Q, what we call Q over MQCD, where MQCD is sort of this fuzzy number that we don't really know what it is, but it's around 1G. I want to talk about the very low energy regime, which is zooming in here. So this pionless EFT, the high scale, is given by the pion mass. And why does that make sense? That makes sense because there are scales in nuclear physics, such as the deuteron momentum, the binding momentum. Because the deuteron is so lightly bound, you have this very low energy state, which in momentum is around 50 MeV. And that's related to the two nucleon scattering lengths being much larger than the typical range of the interaction, which if we take pion exchanges around 1.5 Fermi or so. But the scattering lengths that describe the scattering of two nucleons in the S wave at zero energy, they are much larger. So in the triplet channel of 5 MeV or so, factor 5 larger. And then in the spin singlet, this is very, very close to what we call the unitarity limit, where the scattering length would be infinite. It's like minus 23.7 or so. So those are low energy poles in the S matrix. The deuteron is a very, very shallow bound state. There's a virtual state, or some sort of anti-bound state, and the one is not. That's something that would be bound if the interaction were just a little bit more attractive. And those give you scales, and you can expand in the ratio of these scales.
Can you please explain again where the 50 MeV comes from?
If you take 2.2 MeV, and you convert it to a momentum scale, it's if you're looking at the tail of the wave function.
Okay, so
it has a
MeV per C, not the.
Yeah, it's the square root of nuclear mass times deuteron binding energy.
So it's the 2.2 MeV.
Yeah, but converted to momentum, because that's the tail of the wave function. The fall off scale. So interestingly, these scattering lengths are actually so close to what we call the unitarity limit, for reasons I don't want to go into today. You can actually perturbatively expand around this. You can take a theory where you just set them to infinity. You say the deuteron is a zero energy state, and you expand perturbatively around that. Turns out you can describe light nuclei, energies, and radii in a converging expansion around that. For today, I'm going to just use a standard pionless EFT where you have your low energy scale given by momenta of the order 50 MeV, just set by this, and the pion mass is the high scale. So this is the thing. So this theory in the strong sector that has only contact interactions left. You can think about starting from a chiral EFT and integrating out the pion. That's sort of tricky because you're changing the role of the pion mass. Nobody really knows how to do that, but in practice, you just construct this theory, you constrain it to data or lattice QCD integration. So you have only zero range forces plus electromagnetism, which is relevant today because we're talking about protons and neutrons. But in the strong sector, you have like at leading order, one zero range force for each S wave. There's only a force only in the S wave. And then as you go to higher orders, these are zero range forces with derivatives. So you're sort of building up the range and this sort of multiple expansion around that. Interesting thing that happens here is you have a three-body force at leading order in this theory. This is, I'm going to talk about that a little bit more. This is something peculiar to pionless EFT and it's related to these large scattering lengths promoting the three-body force. It's related to, if it means anything to the Efimov effect, it's something that's described by this theory. The same theory formally basically also describes cold atomic systems where people can actually measure these things. But there's something happening with renormalization that promotes this three-body force, which would naively be higher order, and it is higher order in chiral EFT. In pionless EFT, we have this thing here that leading order. So at very low energies, this is an important point I want to make here, is pionless EFT converges faster than chiral EFT. If you're looking at momenta below the pion mass around 50 MeV, then this pionless expansion is more efficient than the chiral expansion. Exactly where the validity stops is an open question because in practice it does seem to work above the pion mass, which doesn't really make much sense from the perspective of not resolving the pions. So I'm going to be conservative. I'm going to show results up to 100 MeV in momentum or so, so I'm staying below that. But also when you talk about describing nuclei, it's an open question because you don't really know what the scale is. So this is why I leave this open here. So I don't want to go too much into these equations here. Basically, for this part, I'm going to show you diagrammatic equations. I just have this slide here to explain to you what the various things mean.
Excuse me, may I ask a
Yeah.
question? When you say pionless, do you mean that you have either spin carrying part of your interaction that's just zero range? Because pion plays a big role. Like when you calculate, for instance, the gamma field intersections, it's basically sitting on the pion exchange.
There's a current, so you can describe those things. You can take that diagram with the pion exchange, you can collapse it.
Yeah, you just send the pion mass to infinity, basically, but keep this.
Yeah, it's like I said, how exactly you actually integrate out the pion from the chiral EFT is a little bit tricky. In principle, you could do that, but then you have to deal with the fact that it changes from a low scale to a high scale. But in principle, you can do that. But the thing you're talking about is a diagram, like a current, say this is a pion, something coupling here. In the pionless theory, there would be a diagram that looks like this. And there's an unknown coupling associated with this, which you can either constrain from the experiment, but there's also for some of these currents, there's lattice QCD constraints actually.
But why cannot you simply calculate it? What's the problem?
Fun.
And you say you have a pion and then you want to integrate it out.
Yeah, but you're starting from a Lagrangian where you have the pion, like it changes from the low scale in chiral EFT where you have explicit pion mass dependence in these diagrams that scale like m pi squared. And now you want to change to a theory where you only have m pi in denominators because it's a high scale. I'm not aware, probably it can be done. I just don't know anyone who has done it. And I have this conceptual issue that changes the role. Maybe mathematically you can just write it down and calculate it, but I don't think anyone has done that. In practice, you don't need to because there's not much insight really from that because the chiral EFT is also constrained from experimental data. So you can just as well constrain the pionless theory from the same data directly. You know, by symmetry, you have not left anything out. For the pionless theory, there's actually lattice data because it's easier to match to the pionless than to the chiral. So in that sense, it's actually more efficient to use the pionless theory. But yeah, you can relate these diagrams by just shrinking them to contact forces. So I want to talk about this three-body system with a deuteron and a nucleon. I'm going to talk about neutron, deuteron first, and then like show the modifications due to Coulomb interaction. And so one way of writing this down, there's multiple equivalent ways of writing down the Lagrangian for this theory. For this three-body scattering system, it's particularly efficient and convenient to use this formalism where we introduce auxiliary fields that carry quantum numbers of 2 nucleons. So this double line here that you should think of as a deuteron. Normally the theory has nucleons, but you can make a field transformation in the Lagrangian, introduce this thing that has quantum numbers of a correlated pair if you wish. And you can integrate out those fields, you can recover the theory with only the nucleons. But this gives you a way of writing down equations diagrammatically, as I'm going to show you on like 3 slides or so, that is particularly nice and simple. This fat line here is a 2 nucleon state in the spin singlet, one is not channel, which is also relevant. And then the couplings you have in this formulation is the splitting of a deuteron into 2 nucleons or a splitting of this pair into 2 nucleons, and then the HC there, point this way, this is like the inverse process. And you can think about if you have no dynamics in these fields, which the leading order you don't have, this sigma D here is just the leading order coupling, then it's sort of like a trivial field. You can integrate it out because you can solve the equation of motion and algebraically, and you recover directly these couplings just between nucleons. So this is like the fundamental way of writing the interaction. We use these dibaryon fields, we call them just for convenience. The theories are equivalent. And then this, so it's non-relativistic. You see it looks a little bit ugly because we always separate out time and spatial derivatives. And there's a capital D here because I want to couple 2 photons. So it's a covariant derivative. There's a systematic way of coupling this to EM currents. So, but again, I don't want to go into any of these details. I just want to explain what the diagrams mean. So you have to fix these parameters, as I mentioned. A priori, they are unknown as in any EFT, and you need input data. And I said already, you have to regularize first. If something is divergent, then you normalize by fixing, and the running couplings is fixed by these normalization conditions. And it can be experimental QCD. In this case, I want to go into a little bit more detail. What do we fit these things to? So it's non-perturbative. This whole theory is inherently non-perturbative. The leading order is always an equation that you solve, say, I'm going to show it again, it's the Schrödinger equation or Lippmann-Schwinger equation. In this case, to fix these parameters for the 2 nucleon scattering, we have to calculate the T matrix, which is solving the Lippmann-Schwinger equation, and then you massage that into this thing called the effective range expansion. So scattering at low energies is described by a scattering phase shift. You might remember from some advanced quantum lecture, it's just the phase in this asymptotic wave function. And there's this thing called the effective range expansion, which is an expansion of this combination here. The S wave K times cotangent of the phase shift can be shown, and I should put the beta reference here. Beta showed that this is an analytic function of the energy or of K squared. And these parameters here, these are what you can relate to observables. Scattering length is this thing 1/A. It's historically written as a length scale, so it's in the denominator. And then this is the effective range, and then all the others are called shape parameters. So what you do to fix your parameters in this theory is you calculate this thing. You can do this analytically, I should say, because the theory is so simple, you can analytically solve the 2-body problem. You're calculating this, and then at leading order, you're demanding that this is reproduced to some value, which could be the experimental value. And this gives you these unknown couplings, and then it could be D is the deuteron channel, T is what I call the isospin triplet channel, and then the 0 indicates leading order. In this dibaryon formalism, there's 2 parameters with only 1 constraint, so only one particular combination of them is actually fixed. At next to leading order, you're fixing these 2 things independently, because next to leading order, you also reproduce the effective range here.
Why for the sum the sum of the first leading order is negative and the second is positive?
That's nuclear physics conventions is to put the minus sign here. Particle physicists would define the scattering length with the opposite side. It's pure convention. There's really no meaning to it. So in the two-body sector, pionless EFT is just a fancy way of rederiving the effective range expansion from like 70 years ago or so. It gets more non-trivial because you have systematic and you can do many body physics with this. But it's really as simple as that. You're fixing your parameters by these effective range parameters. So that's the input that goes into this in the two-body sector. And as I said, it's because we're doing nuclear physics, we have to generate bound states. It's not the perturbative theory like QED, where you have a finite number of diagrams. Leading order is always non-perturbative in these calculations because we have to generate the deuteron as a bound state. We have to generate nuclei as bound states. You can never get bound states in perturbation theory. And the same is true in chiral EFT, I should say. Leading order is, by my definition, leading order is all the stuff you have to resum. And then if you want to do it in strict perturbation theory, you do distorted wave perturbation theory on top of that leading order, which was non-perturbative. This is the way I'm doing these analog calculations I'm going to show. So it could be Schrödinger, it could be Lippmann-Schwinger, depending on what problem you're looking at. So what has been done? This is just a little bit of history because I talked about this pionless theory. It goes back to, say, late 90s, I think is when it came up. Originally as a way of understanding how to normalize chiral EFT, because there's all these conceptual questions. If you have non-perturbative theory, how do you do normalization? So people like Foucault, Bedake, and others, they looked at this, and Martin Savage, Silas here. They looked at this theory initially as just something simpler, because if you don't have pine exchange, theory becomes much simpler, but it turns out it's actually useful. And then very quickly, people started making very high order calculations with this theory. So something like the NP capture cross-section, it's relevant for BBN. You have very, very precise predictions with less than 1% uncertainty by come out of these papers here. Proton-proton fusion can be treated, has been treated, relevant for solar fusion. So for these very low energy capture cross-sections, only the two-body theory is something useful. You can make very accurate and precise predictions. Then as just one other example here, this was Harold Grieshammer with his student at the time. There was a measurement of neutron disintegration at the Dalimak in Darmstadt that they were describing with a potential model, probably AV18 or something, I forget which one. And there was a discrepancy between the data and the experiment, and nobody knew what that means. Then Harold and the student, they did this Pineless EFT calculation, and as an EFT with a systematic expansion, they put error bars on their theory, and they confirmed the potential model. So that's good, but they put an error bar, and then you can unambiguously say there must be something wrong with the experiment. Which with a potential model, you could always, maybe just have the wrong model and you don't know. And in fact, this is a nice example because subsequently, actually, they did identify some issue in the analysis and we reanalyzed them and agreed. This is one of the nice stories to tell there. So talking about correlation functions, for proton-proton, this has been measured before and this is all published, like by Ellis, for example. So we can use Pineless EFT in the two-proton sector. The simplest implementation is forget about all of these dibaryon things. Just think about an attractive Gaussian potential with a certain range, which you can vary because the range of that Gaussian is basically your inverse cutoff. And you put Coulomb on top of that. And then you have like a two-body potential. You can make a predictions, you fit it to the proton-proton scattering length. And you can calculate the scattering wave function. You can calculate the correlation function using this formula that I showed you. And that's in this plot here where I compared the same calculation with the AV18 potential. And there's no data here, but I should say this has been measured. I just didn't find a plot that was nice enough to put here. So this AV18 theory curve describes the measured correlation function very, very well. And then since the Pineless EFT calculation here with one particular regulator, but you could vary that and it looks essentially the same, describes the same. So green curve is the EFT. These dots here are AV18 with only S-wave interaction, and you can add some higher partial waves to see it makes a tiny bit of a difference here, but not much really. So for PP, just as an initial test, have we any chance of describing these correlation functions of Pineless EFT? Yes, it works nicely for PP. That's the main message here.
And these R sources that we should get from high energy physics in principle.
Yeah, so the source radius, I think they actually constrain partly by fitting the data to these models. I use the same source radius here as they used for the AV18 calculation. So this is something I compared with Bhavani's calculation. They have this code they call CATS, where they basically solve the Schrödinger equation and get the same thing with some potential. So I use the same source radius as Bhavani, and this is the one that did give the best fit compared to the experimental data, as far as I recall. This is where this 1.26 is coming from.
Which data?
That was Alice data,
LSPP.
LSPP. Yeah, so this is just a precursor in the two-body sector. It's very, very easy to just set up this theory and calculate this thing and see does it work. And message is yes. So it looks good. Usually people don't, like, there's other calculations where you use the same sort of input. I said I use the scattering length here. That's the only thing I constrain. My Gaussian potential I constrain to reproduce basically the triplet scattering length. This goes back to this Lipnitsky or Lipnitsky-Lubovich model, where they also basically just take the scattering parameters and they say, let's assume the asymptotic scattering wave function is valid everywhere, including short distances. And then you just put that in your correlation function and you get out some expressions. The asymptotic scattering wave function, this is with Coulomb, F and G are the regular and irregular Coulomb wave functions. It's sort of like a Bessel function with a Coulomb distortion. For those of you who haven't seen this, like this gazillion papers on analytically known results for Coulomb. These wave functions are one thing. This delta here is actually the phase shift relative to the Coulomb wave function, not relative to the free case, because for charged particles, they're never asymptotically separated. Anyways, the main message here is what goes into this Lipnitsky model is also the scattering length and the effective range. And you can go through that, you can make a prediction. Looks very much the same. So in this sense, Pineless EFT, again, is a way of systematically recovering this model where you just use scattering data, low energy scattering data to constrain your prediction in the two-body sector. In the three-body sector, so this is what they first, this is now actual data. I'm allowed to show this because it's Alice preliminary approved.
Do you have anything to say about the neutron correlation?
I could calculate that, yes, but there's no experiment.
There is experiment. Fortunately, it's not well defined. It's very large.
Oh, you mean the scattering length is, yes. So, okay, that, yes, we can say that there's actually papers in Pineless EFT constraining using the trinucleon energy difference to constrain the NN scattering length. That's another example of things I could show, but this is like partly correlating the three and the two-body sector. As far as I'm aware, like something around -19 is fairly accepted as NN scattering these days. Yeah, in principle, we can say.
You cannot determine the sign.
So Pineless EFT does not predict the neutron-neutron scattering length, but the best you can do is that I know is you can use the correlation between the difference in PP and NN scattering is correlated to the difference in helium-3 and triton binding energy. But it's not as constraining. Actually, I have a paper with Hans Hammer where we show that from that perspective, Pineless EFT actually does not even exclude that the dineutron might be bound. So it's not very constraining, but it's constraining.
That's why it was the next question. We don't know about the binding.
Yeah. But we can show that at least Pineless EFT does not say it has to be unbound, which is, I can show you the paper if you're interested. Here, this is now PD correlation function. You see the experiment is down here. I have a backup that we zoom in there. This is this Lipnitsky model for PD. Like using different, like there's not terribly good agreement from experiment, what's the value of the scattering length there. So they're looking at a bunch of different references. This is a theory calculation. But the main message here is the data is down here. The LL prediction for the correlation function would be up here. So I think it's fairly obvious that this is not working. So the simple two-body model does not describe the PD correlation function.
Just to back up, maybe this is a stupid question, sorry, but what's K here? So this is the relative momentum in the rest frame of a pair of particles?
Yes, in the center of mass frame.
Center of mass frame. Okay, so it's not. Yeah. So this is you're comparing to Ali's data, but this isn't like in some lab.
Yeah, this is like the transverse momentum in the center of mass frame of the 2 points. Sorry, I should have said that.
Thanks.
So for me, it's always the same.
Small r. It's a conjugate to the small r.
Yes, yes. Small r is the relative coordinate, like absolute value of it. This is the conjugate of that.
But the correlation function is normalized to unity is there's no correlation. So
Yeah, at high energies, that's always true, even with the anti-symmetrization. So it goes like they both go the data, and this data is probably already corrected for acceptance and baseline and like all the things they do. But the point is like the interesting stuff is happening here, but the LL model is up here. So this is just as another motivation. Why do we want to do a full 3-body calculation of this thing when in principle there's this LL model and it's a 2-body final state? Why doesn't it work? And well, it doesn't work. Just from compared to data, there's no way of reconciling this, I would say. So we want to calculate this, and I'm going to go through this in steps. And again, I'm going to show you, in this case, for once, I'm going to show you the diagrams and the equation that follows from it. For the rest of this part, I'm just going to show you the diagrams because it gets subsequently a little bit more complicated because we add more stuff. So with these baryon fields, and again, the double line here, two cursors, move one. The double line here is deuteron. We have to make a choice of what channel we're looking at. This is a, say, we're looking at a relative S wave between the deuteron and, in this case, it's a neutron. There's no Coulomb here. And we have to say what's the total spin. So this is the equation structure in the spin 3/2 channel. So spin 3/2 has, I'm going to come back to that on the next slide. This is the simplest equation you can look at because the spin basically prevents this 1s not intermediate state. So it looks like an effective 2-body equation where the driving force is this one nucleon exchange diagram. And then this blob here, that's the scattering amplitude we want to calculate. And then this is an integral equation because the blob appears on both sides. So it's an inhomogeneous integral equation. This, what we call the kernel, is basically this one nucleon exchange diagram. Then you have this intermediate propagator here that has the full 2-body dynamics. This is not just the same, we're using the same thing to draw it, but when this is in an intermediate state, it's actually a full infinite number of splittings and recombinations you can put in. This is the full 2-body T matrix and Weeds function. So that you can get first, and then you have solved the 2-body system, you insert the 2-body solution into the 3-body equation, you get out this 3-body scattering amplitude. What I just mentioned is that's the simplest way of writing it because you can couple the spins of the deuteron and spin 1, a third nucleon and spin 1/2, so they can couple to spin 3/2, total spin 3/2, or total spin 1/2. In this, what we call the spin quarter channel, where it's a total 3/2, there is a projection that is maximum, which is like all spins aligned. And then from that, you see that in that configuration, it's not possible by Pauli principle to have this spin 0 intermediate state. In this other spin channel where you have the spin total spin 1/2, you always have like 2 of them aligned and the third one anti-aligned. And then you can have a spin 0 intermediate state. So what happens is the calculation becomes a coupled channel equation because this amplitude here, nucleon deuteron going to neutron deuteron, is coupled to nucleon deuteron going to this 1s sub-intermediate state. Plus this is not an asymptotically observable state here, but it is an amplitude that appears in your equation and you have to include it, you solve this, and then the extra thing you get out is this blob here. And then there's this thing about the 3 nucleon force. I didn't draw this. So in this spin doublet channel, this equation structure here, in principle, there's another driving diagram, which is just a contact interaction. It looks like, sorry for the fourth and zoom, I don't see the board, I guess.
You can write on the touch screen if you want.
I could try.
If you want to annotate on your slides.
So there would be a diagram here, which looks like this, and then it's also iterated. Well, then you have this contact force here. So I didn't draw these because it's sort of obvious how they look like.
Yeah, there's magnets everywhere.
Okay, that did not work very well. Apologies for that. Anyway, this force is there for reasons related to this Efimov effect, or you can actually think about it in a simpler picture. in the spin double channel, there's the triton as a bound state. And this is basically fixing the binding energy of the bound state, because that triton is actually, it's been shown, it's sort of, if the scattering is infinite, there would be the Efimov effect in that channel, you would have infinitely many bound states. There's only one and one virtual state left in nature, and you adjust this 3-body force to fix the position of that
Maybe
state.
it's a question. Right now, if you give me the bound states, what about Thomas collapse?
Without the 3-body force, you would also have the Thomas collapse.
Yeah.
If in the limit where the cutoff goes to infinity, you also prevent that already because you have a finite cutoff for any given calculation. You vary the cutoff, but it's always finite in practice. So yes, that would happen, but sort of this 3-body force is also balancing that. So you're fixing the physics. After you put in the 3-body force, you're predictive. You need one 3-body input. Say you put as input, you use the triton energy, but then you're predicting doublet channel neutron-neutron scattering at all energies. And you can take your cutoff to infinity through normalized. It's just related to this Thomas collapse. In fact, that you need this 3-body force here at leading order.
So you manage at the cutoff and then 3-body force.
Yeah, the 3-body force also, it varies actually wildly. I have a backup slide for that. Maybe we can come back to it later.
Yeah, just a short comment. You were asking me what relativity when I was talking. So actually, relativity process is something like a 3-body repulsion
Yes,
that also helps to avoid Thomas collapse.
yes, that's correct. Even in chiral EFT, you don't even need relativity. If you have pi exchange, it regulates the same thing. I should stress it's not a surprise that there is a 3-nucleon force. There's always a 3-nucleon force because it can appear. It's just that naively one would think it should be subleading order, and it is in chiral EFT. The unusual thing in Pineless EFT is that it's a leading order effect. And it does provide. Okay, there's the comment. So this is the equation structure you would solve for the neutron-deuteron system in the spin doublet channel. And then it can be any angular momentum. I'm just talking about spin coupling, but you also have angular momentum. So it could be in relative S wave and P wave and so on. And all of those channels, or at least the S and the P waves, have to be included in these correlation functions because the experiment just averages over everything. Okay, so we have this thing, and it's there. It's just not explicitly included. And this paper here was the main result that showed that this is required of leading order. Okay, finally, Coulomb. So we have charge particles, we have the proton. I have this covariant derivative in my effective Lagrangian. The way you include Coulomb is you would fix a gauge. You have like your photon field. You can show then, again, I don't have this on the slides, but you can show that the dominant contribution, and you can derive this systematically, is a diagram that looks like this, which is just a static photon exchange. So no retardation effects here between two protons. You get the transverse photons with the retardation, but they come in at, I think, like next to the order. It's like a very high order effect. The dominant is exactly what you would think naively. It's the static Coulomb potential. So that doesn't come as a surprise. What the theory gives you is that you can systematically fix your parameters and say in a power counting, there would be corrections eventually from these transverse photons, but you have like systematic arguments why you can do the simple things at the low orders, and you would include the rest in perturbation theory. In practice, because I'm doing the calculations in momentum space, this 1 over q squared is basically the 1 over r, the Fourier transform of 1 over r. In practice, we put a small mass here as an infrared regulator, and we have to probe that the results you're getting are not sensitive to this. This is really just changing the Coulomb to a Yukawa with this very, very small mass, and you have to take the limit where the thing goes to 0. This was part of my, not even PhD, but part of my work on my diploma thesis in Germany with Hans Hammer to do this proton-deuteron scattering calculations. So in some sense, this project is interesting because it goes back to the very first things that I was doing when I was starting doing research. And we've shown that this is well under control. This is the main message here. So you can take the limit even when this goes to 0. In the calculations I'm showing here, I picked as like 0.2 MeV or so, very, very small. I don't even have to take the limit because it wouldn't really vary, I know from experience, but that's something that you still have to check for. And in the two-body sector, you actually, for two protons, you get the Coulomb modified effective range expansion systematically, and you can fix the parameters for two protons. So this is then how the equation is modified. Again, I'm starting with the spin quartet here, where we don't have this spin singlet intermediate state. You're just adding a diagram where the photon couples in any possible way. And in this case, we can go across the nucleon exchange, or we can form this bubble here. The way you do the calculation, you can derive analytic expressions for all these diagrams. You put them into a big matrix equation, you solve it, you get the things out. And then you can make predictions for scattering phase shifts, PD. This is the old papers. In the double channel, I'm going quick here because the details really don't matter too much. You have this additional fat line here, the singlet state. The singlet can actually be 2 protons. So now you have to separate out the 2 proton component. You have to separate the isospin basically, because the 2 protons can also have this sort of diagram, which is new here. Like they split and then the photon goes into the exchange, like from that proton up here, going to the exchange proton. So all of this has been done years ago, is well known. What I'm going to focus on then for the remainder of the talk. There. Oh, okay. Is like, how do we get the correlation function? Because there's a little bit more than you need to do than just this. I'm going to skip this. There's a bunch of work in the 3-body sector. You can look at my slides if you're interested. It's just a selection of results, what has been done, including work by myself and collaborators. I want to move fast forward here. Like one comment that we solve the equation with the photons non-perturbatively, which is in fact, if you're interested not in the lowest regime. So the Coulomb force is interesting because it has an effective strength that depends on momentum. If you have very low momenta, then it's really dominant. It goes like 1/k. So for very low energy scattering, it's a it's dominant interaction. It completely overwhelms even the nuclear interaction, basically. But at higher momenta, it's perturbative because it goes like 1/k. In this paper here, we showed that above k equals 20 MeV or so, you can actually start with neutron-deuteron phase shifts and do the perturbation theory, even in the Coulomb on top of that, and we describe potential models and experiments. Keep in mind, when I compare the correlation function for ND to PD, that we would actually expect those to be perturbatively close at high momenta, just because Coulomb becomes more and more irrelevant, and the isospin ranking in the strong sector is relatively small. So let's reflect before we move on. We have a theory that can calculate proton-neutron scattering. It was phase shifts. Scattering phase shifts is all we did, because that's typically what you get from these phase shift analysis from experiments. Pineless EFT captures precisely what is relevant at these low energies, and is relatively well understood, and it's well understood and relatively simple. That's the way to say it. So we need to work a bit harder to actually get the correlation functions, because things like the anti-symmetrization and so on, they matter, and also the precise formalism we use in the 3-body sector. So this is the part I want to talk about now. And now I switch from the diagrams to the Faddeev equations, which is the historically older way of calculating these 3-body scattering systems. This is the most technical, but I'm trying to go a bit, not too fast, but I'm not going to go into all of the details. So you can see I'm adding equation numbers here, so it gets a bit more hardcore. I want to go back to 2-body before I talk about 3-body, just to get the general idea, because we're doing all of these things in momentum space, but you're probably more used to thinking about wave functions in coordinate space. So in the 2-body sector, if we talk about scattering, and this is the slide I could maybe have put at the beginning, the scattering wave function, this is how you would see it in a quantum lecture, is you have this incoming plane wave, and then you have an interaction at the scattering center here, and you have outgoing spherical waves with angular modulation. That's the scattering amplitude. So square this fk of theta, that gives you your differential cross section. That's how you would define this. And then the scattering phase shifts is what you get from making a partial wave decomposition of this cross section. But it's related to the scattering wave function in this way. So this is in 3D, but you can write this down in partial waves. Basically, you have the plane wave expansion in Bessel functions. You get a Bessel function plus this thing already is spherical. So you solve the Lippmann-Schwinger equation. This is my one-slide derivation of the Lippmann-Schwinger equation. And in the interest of time, I'm not going to go through it in very much detail. It's just as a reminder, because I assume that at some point everyone has seen this. We make an ansatz for the scattering wave function that satisfies the boundary condition. You would assume that if you switch off the interaction, it's a plane wave. If you go far away from the scattering center, it should again become a plane wave. This is without Coulomb. So you make an ansatz for the scattering wave function. It's just rewriting the Schrödinger equation with the boundary condition built in. You get an equation for the scattering wave function that looks like this. So it's a plane wave plus this interacting part with the Hamiltonian. This is a free Green's function here. This is the potential. And this is called the Lippmann-Schwinger equation for the scattering wave function. And then from that point on, there's like when people solve two-body problems, there's two ways of doing it. One would project this equation into R space, and then it's called the radial Schrödinger equation. You do it in partial waves to solve a 1D ordinary differential equation. You get the scattering wave function. In momentum space, you define this thing called the T matrix, which the easiest way, and this is, I think, following Sakurai. Sakurai does it this way. I think this is the way Hans Hammer did it in the lecture I saw. This is why I use this. So you postulate there is an operator called T, and T acting on a plane wave is the same as the potential acting on the full wave function. And then you insert that into your equation, and you get this equation here for the T matrix with the state K here. It's a plane wave everywhere now. And then you postulate that this is actually an equation at the operator level. You can say from some completeness argument, if it's valid for all plane waves and they are like a Hilbert space basis outside the Hilbert space, you can say it's an operator equation that looks like this. So Lippmann-Schwinger equation is just that, and there's the Green function and the potential. And diagrammatically, it would look like this, actually very similar to the three-body equation I showed you. So this dot here is like any potential, doesn't even have to be Pineless EFT potential. And then the blob, the gray blob here is the T matrix. And you can map this diagrammatic equation directly to this operator equation here, except I wrote the T on the other side, which is okay. So scattering wave functions, then and we want to do it in the momentum space. This T matrix treatment, that's the thing that's easiest to do in momentum space. And we want the correlation function, we want the scattering wave function. But this is a slide relating the T matrix to the scattering wave function. If you just massage these expressions that I just showed you, you arrive, and I leave this on the slides if you're interested in details. I'm just going to discuss the final result here is that this matrix element here is the T matrix divided by this sort of energy denominator, which is just a Green's function. So you can get, where's my equation? This is the momentum space representation, equation 5 here of the scattering wave function. It's a delta function. So the plane wave part in coordinate space becomes a delta function in momentum space. This is the part you can always treat analytically. And then you have this matrix element here, which is a half off-shell T matrix. This is interesting because when you solve the Lippmann-Schwinger equation as a matrix equation, you discretize your momentum integrals, you get just an algebraic matrix vector equation. You anyway get the half off shell. You're actually only interested in the point where the momenta are equal, but you always get a vector just from the way you're solving the equation. That half off shell T matrix is essentially the scattering wave function in momentum space, minus the plane wave part, which is always just a delta function in trivial. So we have a clear way of getting the wave functions from the T matrix. But we can actually also just stay in momentum space and define the correlation function in momentum space. So I'm going to skip over this. You can just take the Fourier transform of this Gaussian, and it becomes another Gaussian with two momenta because you have in and outgoing, and you have some modified Bessel function here. So to do the actual calculation, you never really need to go to R space. You can just say in momentum space, evaluate the correlation function. And this is the way I do this is I just write the correlation function as the expectation value of some operator. So this integral here, if the operator is local, then you get this expression. But in general, this S of R can be an operator S hat evaluated between the wave functions. Also nice to write it this way because when we see expectation values of operators, that we a bit more faith that they're actually observable. And yeah, we do this in momentum space, the main message here. And now we have to do this for 3 particles. So we get the T matrix for the 3-body system. We get the scattering wave function in momentum space, and then we get the correlation function. And I'm going to be brief here and move forward to results. So we solve Faddeev equations. And then I should stress, we're actually doing the diagrammatic. I want to bridge here between the diagrammatic approach and the Faddeev equations because they're just equivalent. The diagrammatic approach exactly recovers the essential part of the Faddeev equations for a certain form of writing the interactions. The idea is we have a three-body system. This is for a bound state. We write it in a certain way, and we get basically this P here is a permutation operator that recovers these nucleon exchange diagrams. I'm sorry for being brief here, but I don't want to go too much over time. And there's so the final equation for a bound state would look like this. This psi here is one Faddeev component. You need three of them, permutations of this to actually describe the full wave function. There's the free Green's function, there's a T matrix, there's the permutation. This is basically this nucleon exchange diagram. And the T matrix here, now written in lowercase, just by convention how people usually write it, is this intermediate propagator that I drew, the double line or the thick line. That's this T matrix here. For scattering, we put an inhomogeneous part. It looks very much like the Lippmann-Schwinger equation. That's why I started with that. So this phi here is a deuteron wave function capturing the structure of the deuteron in relative momentum with a plane wave with a third nucleon, which again could be a neutron or a proton, and then you would need a Coulomb function in some partial wave. And then you get this Faddeev equation for this I call T tilde because it's slightly different convention from the standard literature. You have an inhomogeneous equation, you do the same thing, details don't matter, you get out the scattering wave function. Because you can do the same thing, you can relate this T tilde to the scattering wave function exactly as in the two-body sector. And then you antisymmetrize, coming back to your point. So this is only one component. Out of the calculation, you get one Faddeev component, but you need to anti-symmetrize the whole system. In the diagrammatic approach, you don't do that because it turns out the scattering phase shift is already completely defined by just one Faddeev component. And normally when you describe, say, cross sections or scattering phase shifts, this is all you need. But for this correlation function, we actually want some part of the short distance structure of the wave function. So we need to do this step to actually do the full calculation. This is the main point of the slide. And to understand how to do that in the diagrammatic formalism, I went through the whole Faddeev formalism to relate the two because this T tilde is related to the blob I get from the diagrams. So that's the story there. And the details will be written up in the paper that's forthcoming. But as of now, none of this, like my slides are the best you can get for the details. So why all this? As I said, this T can be related to this calligraphic T. That's the thing that you get from the diagrams. And the actual construction of the full wave function is sort of simpler to discuss in the full video. So the strategy, this is now what I want to focus on. We solve the integral equation from the diagrams. We have the full dynamics in the ND system. Then we do a straightforward conversion to this T tilde because in that formalism we know how to anti-symmetrize, and there's a bunch of technical stuff that I'm not going to talk about. And then we get the momentum space wave function from the T tilde, and this includes the anti-symmetrization. Then to normalize this thing, you put a factor of 1/3, and then you use this momentum space version of the source function to get the correlation function. So this is the last step. This is the same thing before, and now one detail here, I'm going to wrap up in 10 minutes, I think. One detail here is that we have a three-body state. So we have to produce three nucleons, or we have to produce a proton and a deuteron, right? So we need three nucleons overall. And then there's this paper, relatively recent from Morozhinsky, discussing like the general formalism. If we're interested in this PD correlation function, we have to produce the three, sorry, this should be R3 here, the last one. We have to produce the three nucleons and then have the full three-body wave function. This is including still the center of mass. So we're first doing a transformation because the overall center of mass doesn't matter. Really only depends on two Jacobi coordinates. But what I want to point out here is we have to form the deuteron. So Morozhinsky defines this deuteron formation rate. This is like the expectation value with the deuteron wave function. So this is a bound state wave function and the scattering one, and you have the sources for the two nucleons forming the deuteron here, and we have to divide this overall expression by that to get the correlation function between P and D. So we're following this formalism here. And that's where it deviates from the two-body, because for two-body, you just form the two and then you run with them. But for three-body, you have to account for the fact that you need to form the bound state. As I said, we do this in relative coordinates, specifically Jacobi coordinates. We have our operator here, which again depends on this capital R, which is the source radius. We run through this. In the end, we calculate these matrix elements, and we can calculate the AD in the same form as everything in momentum space. Perturbation theory. This is the one thing I want to show in more detail because we have this perturbative EXT expansion, right? I mentioned that we have leading order, next leading order, and so on, and we have subsequently more input as we go to higher orders. So we want to, I'm going to next leading order for the purpose of this talk. So this expansion in the theory gives us an expansion of the T matrix. Expansion of the T matrix gives us an expansion of the scattering wave function. Likewise for the deuteron bound state, it also changes as you go to higher orders. We get the leading order where we have the leading order wave function with the operator, and we have the leading order deuteron formation. That's simple. We divide out this AD here. And next to leading order, we have two contributions because we get this overall expectation value twice the real value of putting like the NLO wave function on one side. This is strict perturbation theory. We're discarding everything that would be strictly higher order. But now this has two contributions. There's one, which is the one we're interested in, which is the NLO-P decorrelation function multiplied by the leading order deuteron formation times the NLO deuteron formation plus the NLO deuteron formation times the leading order C of K. So to isolate this one that we're interested in, we calculate the overall thing, and we know already the C naught here from the leading order calculation. Then we calculate the AD1, we subtract that term. In the end, we divide by this. So there's like a straightforward procedure to isolate the NLO correction that we're actually interested in. So it's a little bit more work, but this way you have like a strict perturbative expansion. You know you have not artificially resummed more than you would need to. It's like really strict perturbation theory on top of the non-perturbative leading order. Okay, results. This is the leading order P decorrelation function, and I'm varying here the source radius. Let me explain, like the plots all sort of look the same. I can go through them quickly if I explain one of them. So I'm varying the source radius here within a range that we believe is covering what we would find in the experiment. And you see from my wording, I know how it fits to the experimental data, but I can't show you that particular plot. Anyway, so we varied this from 1.1. This is all in Fermi. This is leading order. You see, it definitely looks different from this Nitschke model because now we actually start at 0 and we stay below 1 here at the low momenta. So in that sense, it looks much better. There's a dependence on the source radius. In practice, you would pick a source radius and try to see which source radius fits the data best. Or you have a different way of constraining the source radius and put that in, and then you vary it a little bit because of uncertainty quantification. So you see, it looks like this. This includes S and P wave interactions. And then it includes free Coulomb on top of that. So we're actually summing to L equals 15 here. But the actual interaction is only included in S and P waves. Because in this momenta up to 100 MeV, I think that's like a tiny contribution from the D wave, but you really don't see it. Like it's a hierarchy of partial waves, just like it is in the cross section. It's the same physics reasons. So S and P, we are summing over spin doublet and spin quartet and so on. All of this is included, and this is what it looks like. If we include the NLO correction, and here I only left like one, like the central source radius for the leading order. If I go back and forth, you see I leave that one line, and we see the NLO shifts it upwards, but not very much. So this shift is actually consistent with what you would expect from the Pineless EFT expansion. This Q over M high is about 1/3. So it's less than 1, but it's not like QED where you have like alpha is 1 over 137. It's like a relatively slow converging theory.
Why the correlation function is collapsing to one point independent of
R? It goes, so before
go one back.
It goes, if I were to go to higher momenta, I have the calculation up to 120. I don't have the plot here because I wouldn't trust the theory there necessarily. But they diverge. Somehow the source radius like around 100. The same thing seems to be happening with AV18. We don't know why. It's just it happens. But it's not like they stay. Like if you go to larger K, they would spread.
But again, yeah, that's why I asked what's special about this point.
Can't give you an answer. We've observed this. It doesn't seem to be coming from the EFTs because, as far as I remember, Michael's AV18 calculation, there was something very similar happening there. I would not go as far as contracted physics in that, but it's interesting. It's peculiar. That's sorry, it's the best I can say. Okay, so it shifts it upwards. and it shifted upwards. Importantly, the shift here is consistent with the 30% uncertainty we would expect at leading order. We can do better here. So this was one particular way of fixing the input. Because I was driving on this earlier today, I should make the point here. What we can do is, this was fixing the deuteron binding energy instead of the scattering length. You can also fix the scattering length, and the difference is about 30–40% in the two-body sector. So to do UQ, we would vary the input parameters here. Also, in the spin doublet channel, this actually fixed the neutron-neutron scattering length. We could instead fix the triton binding energy. So we would be going back and varying the input, and we would expect some variation in the correlation function at leading order, and then that should be of the order 30%. Should be consistent with the shift we could see from leading to next to leading order, and this is roughly a 30% shift. So it looks like the theory is actually doing what it should. I highlighted here, this is a prediction with very few input parameters. It's actually at leading order, there's 3 input parameters, two scattering lengths in the two-body sector, actually 3 with a proton-proton because of a little bit of isospin breaking. So it's 3, let's say that. And 1 3-body force, because this 1 3-body parameter, because the 3-body force is just a constant times its diagram. It's the simplest 3-body force you can think of. So there's 4 strictly input parameters at leading order, and 1 more at 3 more at NLO. So the source radius is a free parameter in the theory calculation. It needs to be determined from experimental data, or they do these looking at transverse mass distributions. They have some way of estimating the source radius, at least a rough value for it from the experimental data. And then to really constrain it, you would take this theory curve and vary R and fit it to the data, also correcting for, you might not identify all the deuterons, like there's a bunch of corrections they do to the data, I should say. And this is what Bhavani is working on, for example. There's another question I want to raise here. This is the discussion point that I want to bring up. So you can ask the question to what extent this correlation function is actually observable. So I wrote it as this expectation value between wave functions, right? And we see a good agreement using different potentials. We see convergence, we see description of the data. But clearly, if you put the source radius, if you make the source radius and let it go to 0, you would effectively probe the wave function, the scattering wave function at very, very short distances. And we know from this EFT paradigm that is not observable, because we can change our cutoff and it would change the short distance wave function arbitrarily. And scattering data does not constrain this, because the scattering phase shift is always the asymptotic wave function. So certainly within these regime of source radii, it seems to be working well, but then there must be a reason why can't the source radius go to 0. Maybe there's a straightforward reason for that, but I want to highlight this here. We should check for this, like as I increase my cutoff, does this thing converge? Because for the higher cutoffs, I resolve more of the short distance physics, which in principle the theory does not constrain. And certainly if I put this source radius to 0, which does not seem to describe the experiment, but think about it. So you have to wonder, like, what's the proper way of defining this? And there's a relation to things like short range correlations, where you can also think of changing your interaction, and changing the cutoff is changing the interaction. So we just put one source operator. I'm not varying the source operator when I vary the cutoff, but probably there's some more microscopic way of describing the source where you could do this thing consistently. So this is more of a discussion point, just some note I want to put in here. We have to wonder to what extent is this thing.
The size of a proton don't limit how small R can be. It cannot be much smaller than the size.
I would think so, yes. So maybe in this case it's simple, but there's like related questions because when you probe very short range correlations that were brought up earlier today, also what about distance scales that are smaller than the size of the proton?
Yeah, but in the very high energy scattering, our understanding is that it will scale for the size of the proton, which is like half or smaller than the charge radius. So effectively, a very small scale. But then this is for something larger than that, some way.
Yeah, so we don't see, so I can to some extent I can answer the question here. So this is varying the cutoff from 400. These orange like curves are the same as all leading order. Going from orange to green is still the 800 MeV. And I have done like part of the calculation for a higher cutoff. I see there's not much changing beyond 800. So this thing seems to be converging with the cutoff for this range of source radii. It looks good, but there's fundamentally this question here. So you see
There
this,
is no constraint from data here. Is that what you're telling me?
in this case, there's no constraint from data. Bhavani
What
has
happens?
been,
Yeah, okay.
yeah, so Bhavani has been using these interactions and AV18 from Michele to fit it to the data.
And,
It looks pretty good.
but pretty good meaning all of them fit well?
No, for, so the central one here is chosen for the reason because that's the one.
So that's why you showed earlier on the 1.36.
Yeah.
1.36.
Yeah, so so Michele, I should maybe have this on the slide here. So the PISA group is working on the same calculation in a completely different formalism. They use hyperspherical harmonics, it's a different way of solving the three-body problem, and that's in our space. They use the AV18 plus some three-body force in the same calculation. That actually describes the data very well, even up to much larger momenta than I'm showing here. The Pineless EFT is constrained to the low energies. You cannot really expect this to work much beyond 100 MeV. I would say, even if it does work, you would have to wonder why. Right? So I'm being conservative here. But part of the collaboration is working on this AV18, and they go up to 200, 300, or maybe even more MeV. I forget how far exactly they go, but with that potential, because it's a very high resolution potential, you would assume you can do that. You don't know the uncertainty for that because it's just one potential model, right? So, but we're looking at this combined with the EFT because we can compare the two in the low energy regime where we believe that both of them should be applicable and see how well does it work. So this is for ND. I'm showing these numbers because for ND, I can actually do the AV18 calculation with the FDF code that I have. For this talk,
This is AV18 plus Urbana?
they are working on AV18 plus Urbana. This is just pure AV18.
There's no Urbana correction.
There's no Urbana here because I don't, in that code, I don't have the three-body force.
Is the Urbana correction important here?
You can look at the numbers. So I think it's slightly important because it would shift the spin doublet contribution, which at the very low energies is actually the dominant one. So the doublet S wave is strongly affected by the Urbana because it shifts the triton to the right place, basically. So you can see from the numbers, this is like just at 3 momenta, I put a table here, Pineless leading order, Pineless NLO for ND. This is why these are larger. I'm going to show the plot as the very last result before I wrap up. So the Pineless NLO is within 10% of the AV18 with the caveat that the Pineless NLO actually fixes the triton and N3. So this is a bit more constrained actually because there's no Urbana here, but within 10%, they agree.
So you say that within 10%, the three body forces is not important?
It is important, I think, but the uncertainty estimate for Pineless NLO is 1/3 squared, which is 1/10, which is 10%. So within the EFT uncertainty, this is perfectly consistent. That's my main
You're
point.
in that set.
This is like EFT, any EFT value you see, you should always think about within the uncertainty because the central value alone doesn't tell you much. So I'm showing just values here, but the uncertainty you would expect is of the order 10% from the expansion. And within that, it seems to agree. So this is finally proton versus neutron. So this is leading order. The green is the same as before. I just put in symbols in addition here to make them a bit easier to read. So you see at the larger momenta, they're almost the same and they're actually converging closer and closer if I go on, which is consistent with Coulomb is small effect correction and strong isospin breaking PP versus NN, and that one is not as small. And then experiment probably won't be able to measure this anytime soon, but in principle, make a prediction for. So it goes up, and the suppression you see here is really the Coulomb repulsion. Coulomb basically sends the wave function to 0 at short distances because it's repulsive. And NLO looks similar. This is just for one source radius, the 1.24. And again, these shifts are consistent with what you would expect. And this NLO here actually fixes the helium-3 binding energy because for randomization reasons, again, there's a promoted 3-body force. This is this paper here from 2014, which has more input. Okay, with that I'm done. So as a summary, we have these high energy collisions as an interesting tool because you have this big bang and you get on this low energy information, which personally I find fascinating. And to study these systems, we can look at 3 nucleons as a precursor to actually looking at hyperon, and the Proton-deuteron is going to be in this paper, for example. And we find that for identical particles, a full treatment of these dynamics is really important. And Pineless EFT can make predictions for these things based on very few input parameters in a systematic and uncertainty quantified way at low energies. So to do is, Alice has taken analyzed data, so there's a paper that's within the collaboration just like 2 weeks ago submitted for review with these things. Then, as I said, the PISA group is doing the AV18, so we're writing a joint theory paper to accompany this because it would get too much in an appendix. There's so much formalism, as you could see from my talk. So we're writing that. And then, in principle, you can do PPP. You can do Deuteron. I have a Fadeev-Jakubowski code. I have the dream of actually doing the correlation functions of that. There's no Coulomb in there right now, so it's a bit more in the future. But in principle, we can do this. And then we can also do with the neutrons, like stuff that only theory can do, but it's still interesting.
Take the party, try the format ones.
Yeah, and I have another 4-neuron project. I can talk about that another time.
That's too many points.
Okay. No. Okay. 4 is not so bad.
Four is good?
That's interesting.
I've been told anything more than 2 becomes complicated.
Well, we're looking at different
I know.
methods. Anyway, so yeah, that's all I had. Sorry for going a little bit over time again, but
Thank you. We will continue this discussion this afternoon, but are there any quick questions right now?
Can you put the lambda T correlation? Lambda T, have a tried out like that.
I think they should have this for lambda. They have data that's published and analyzed. That's the work of Jochen and Bauer. Deuteron lambda, I don't know if they have that, but probably.
Can you do a prediction in your model side?
In principle, yes. So I have a Fadeev code. I could put in lambda particles there with some work. And so I don't have this calculation. It won't be tomorrow, but in principle, it's something we can calculate.
So if you go back, like I think this one slide. So I think if maybe one more where you have this plot with leading order and mixed leading order. The data already, I think, reaches 1 at this point. So are you concerned? I know you're most interested in this very low K region, but eventually ask them to 1 or
It would. I'm just not going higher, and it does stay below. So I should say. So I know the analysis compared to the data, it does stay below that. It stays a little bit below the INT, but within the uncertainty, it looks good. It goes a little bit higher because there's like a baseline because you don't identify all the particles. And the way Bhavani is doing the analysis is actually rescaling the theory instead of rescaling the experiment. And they do that by looking at the experiment at large K, because they know it should go to 1, and then they're trying to extrapolate down. The way we do this, because in principle, he would want the Pineless EFT calculation at like 300 MeV, and then do the baseline fit for the Pineless. But I would never trust the theory. The way we do this combined analysis is that they actually do the AV18 calculation for the baseline, and then we apply the same baseline correction to the Pineless results.
okay.
Which you might think of, yeah, it's mixing the two things, but you could also just apply the baseline correction to the experiment, which I think makes philosophically makes more sense, and then the data would come down.
Yeah.
But the way it's presented is that that this Pineless calculation, when Bhavani does, and then he does the fitting of the source radius variation, and we show some band. So the data would get shifted up a little bit. It still stays below the AV18, but I'm not concerned because of this uncertainty in the EFT.
Okay, well, thanks again. Session. We'll come back at 2 for discussion.
Not here, the other one.
Yeah, right next door is probably what we'll do. We can choose whatever we want. I mean, we've owned the building today. No one else is here.